Okay, so let's do some examples using the Reynolds number. Examples with the Reynolds number. And first, let's ask the question, where is the transition from laminar to turbulent flow for a baseball? From laminar to turbulent flow for a baseball. And when I say where, I mean at what speed. Whoa, what happened? Sorry about that. At what speed? Okay. At what speed? So we will need the viscosity of air at room temperature, which is about 0.02 centipoises. And remember that a centipoise is 10 to the minus 3 Pascal seconds, so this would be 2 times 10 to the minus 5 Pascal seconds. The density of air is about 1.2 kilograms per cubic meter. That's kind of a nice number to try to carry around in your head, that a cubic meter of air has a mass of a little over a kilogram. The diameter of a baseball, which is what we're going to use for the L in the Reynolds number, is about 0.08 meters. And the transition occurs from laminar to turbulent at a Reynolds number of around 1,000. So if the Reynolds number is less than 100, it's laminar flow. If it's more than about 10,000, it's turbulent flow. So we'll take the geometric average and say that, very roughly speaking, the transition occurs at a Reynolds number of about 1,000. So we recall that the Reynolds number is defined to be rho LV over the viscosity, eta. So we could rearrange this to solve for the velocity. Would be the Reynolds number times the viscosity divided by the density times the diameter of the baseball. And if you plug in the numbers on that, you get that the transitional velocity is about 0.2 meters per second. So that's pretty slow, right? If you think about it, it's only moving 20 centimeters per second. That's, you could see that motion easily, but almost all the time when you're throwing a baseball or batting a baseball, all those circumstances, it's going to be in turbulent flow. Let's do another example. Let's think about a dust speck in the air. So I'm sure that we've all had the experience of watching little dust specks floating around in the air. And so we want to know what's the Reynolds number for them, and is it a case that the flow of the air around them is laminar or turbulent. So typical velocity for a dust speck might be around maybe 10 centimeters per second. If you sit and watch one, maybe a little bit less, but we'll use that. The diameter of a dust speck can be quite small. Let's pick a kind of a small one, so 10 to the minus 6 meters. And then we have the density of air and the viscosity of air from up here. So if you plug in the numbers on those, you get that the Reynolds number is about 7 times 10 to the minus 3. Notice that the Reynolds number is a dimensionless number, so we don't have any units to worry about. So 7 to the minus 3, that means we're clearly in the laminar flow regime for a dust speck. And again, that's large in the comparison of the dust speck and the baseball, there are two things that sort of were responsible for moving us from the mostly turbulent flow for baseball to the completely laminar flow of the dust speck. One is that the diameter is so much less for the dust speck than for the baseball. That's the biggest thing. And the other is that the velocity is somewhat, well, actually, that's working. Yes, the velocity is somewhat less, and both the diameter and the velocity appear in the numerator of the Reynolds number. As a final example of the Reynolds number, let's compare the life of a microbe with a human. Compare the life of a microbe with a human being. So first, let's calculate the Reynolds number for a microbe. So the length that we're going to use is the diameter of a microbe, which might be about 10 to the minus 6 meters. Experimentally, if you measure their velocity, they are moving roughly 10 times their diameter per second, so about 10 to the minus 5 meters per second. And we're interested in they're moving basically through water, so we'll take eta as 1 centipoise, which is 10 to the minus 3 Pascal seconds. And of course, the density is that of water, which is 10,000 kilograms per meter cubed. So these are water. So if you plug in all the numbers on this, so Reynolds number equals rho LV over eta, you get that it's about 10 to the minus 5 for a microbe. So like the dust speck, because it's small and because it's moving relatively slowly, it's very much in the laminar flow regime. So let's then ask the question, if you were a human being, so instead of just calculating the Reynolds number for a human being, I want to calculate for a human what eta would we need to be in the same Reynolds number. So that is to sort of experience the flow of air or water, whatever fluid it is around us in the same way that a microbe does. So we'll take our equation for the Reynolds number, rho LV over eta, and we'll rearrange this to solve for eta equals rho LV over the Reynolds number. And for L, we'll take a typical dimension for a human being, maybe about a meter, and we are usually moving at a speed of around a meter per second. Again, this is typical of what you do with the Reynolds number. You're kind of trying to estimate things to get them within a factor of 10, and very often you're only interested in the question of, am I in the laminar flow regime or the turbulent regime? So if you plug in the numbers on this, you get that the needed viscosity is equal to 10 to the 8th Pascal seconds. So remember, 1 millipascal second is equal to a centipoise, so this is 10 to the 11 centipoises. That's really, really high. So let's compare it with a couple of normal substances that you might be familiar with. For peanut butter, the viscosity is about 10 to the 5 centipoises, so this is 1,000,000 times more viscous than peanut butter. To get to this level, you need something called the pine pitch, so that has eta of about 10 to the 11 centipoises. So microbes experience the world in a very, very different way than we do. They're kind of swimming through this incredibly thick fluid from their perspective.